Okay, so here is the schematic. It's a side profile of a ramjet. And ramjets depend on ram pressure. Okay, so you have to take these off by some sort of mother plane, catapult, or other powered flight to get them up to a speed, and then it will basically force the air inside, and then it will shoot out. So these are usually for high speed propulsions, and they don't have any turbines, any pump, none of that. All right, it's just air being forced in through this ramjet. And this is how we analyze this. We're going to go from A to 6 using the thermodynamic properties, using isentropic equations, stagnation equations, to get the performance of this ramjet. Okay, so in this video we're going to look at the analysis of a ramjet. All right, so the ramjet is actually one of the easiest air-breathing engines to analyze. All we have is a diffuser at the front. All right, so we got compression. Then we have the combustion chamber. So we inject some fuel, it combusts. Then we have a converging, diverging nozzle to get supersonic flow out the exit. Okay. Now I haven't talked about diverging, converging nozzles. That'll be in a later video. But just know we can get high speeds out of this exit. Okay. So what I want to do is analyze from A to 6 and show you the equations we can use to calculate the performance of these inlets. Or sorry, to calculate the performance of these ramjets. Okay. All right, so let's look first from A to 2, okay, right before the combustion chamber. What we have is isentropic compression. And you remember from isentropic, it's an ideal case. We don't lose any energy. The entropy change is 0. And we're also dealing with the ideal ramjet. So the static pressures, P naught, or sorry, stagnation pressures, P naught, are all the same throughout the entire process. Okay. Static pressures will change because that's like it's static pressure. Pressure changes. Okay. However, the total stagnation or total pressure, P naught, will remain the same. Okay. So what does this mean? Well, this means that T naught A will equal T naught 2. Okay, because we're not losing, the total energy is the same. It's isentropic. We need to know the Mach number, which is U over C, or you can say U equals M dot C. Okay, and again, speed of sound is the square root of gamma RT. And if you remember, T naught A over TA is 1 plus M squared, gamma minus 1 over 2. And we derive that equation for stagnation. Okay. So we can find T naught A, which will then equal T naught 2. Okay. Which is used in the next step to find that F. Okay. And remember, F is that fuel mix ratio. Okay. And that's needed in the thrust equation and all the performance equations. All right. So if you're given the Mach number and you're given the static pressure, TA, you can find your total pressure, okay, which is in a sense the total energy of the system. You can use that. And we're going to now look at 2 to 4, which we call a constant pressure heat addition. Okay. All right, cool. So how do we do this? Well, we got to find F. All right. And let me just get my... So I want to analyze this for you so you can see where this equation comes from. Okay, so we're looking from 2 to 4, right before the nozzle, right after the diffuser. And we're going to use the first law of thermo, which states dE of your control volume, dt, is Q dot N plus W dot N plus the summation of M dot H plus V squared over 2 plus GZ in minus summation of M dot H plus V squared over 2 plus GZ out. Okay. So in this case, though, there's no mechanical work or power. We're going to assume steady state. Okay, so that means the control volume, which is from 2 to 4, okay, doesn't change energy. Okay, so we're only looking at things going across the boundaries. Elevation changes we'll neglect, as we'll assume it's like center of that ramjet between 2 and 4. Okay, so now what we have is 0 equals Q dot N, which we'll call Q dot in, plus we have two terms coming in. We have the air from 2 and then the fuel coming in. So we have M dot 2, and then we have H2 plus V2 squared over 2 plus M dot of the fluid, or the fuel, okay, HF plus VF squared over 2, and then we subtract M dot of 4, H4 plus V4 squared over 2. Now, we're going to neglect this term because that term is much smaller than the air coming in and going out in that section. And if you remember, we can classify H plus V squared over 2 as H naught 2, and this as H naught 4. Okay, so we got 0 equals Q dot in plus M dot 2 H naught 2 minus M dot 4 H naught 4. Awesome. Okay, now what we can do is we're going to look at conservation of mass, which states that the mass flow rates in must equal the mass flow rates out. So we have M dot 2 plus M dot of the fuel equals M dot 4. And we're going to define M dot F like we have before is, oh sorry, not M dot F. F is M dot F over M dot 2. Okay, cool. So these two, what we're going to do is we're going to plug this into here, and then we will assign this in that. Okay, so let's plug M dot 4 equals to M dot 2 plus M dot F into, we'll call this equation 1. Okay, and we'll put from equation number 1, 0 equals Q dot in plus M dot 2 H naught 2 minus M dot 2 plus M dot F times H naught 4. All right, now we're going to divide each term by m dot 2. Okay, and that's where we can get the F. That's what the F is. So 0 equals, now we have Q dot in, okay, something else that we need to define over here, is going to be equal to the mass flow rate of the fuel times this QR, which is your heating value of the fuel. Okay, so we're going to plug that in as well. So m dot f q dot r divided by m dot 2 plus h naught 2 minus 1 plus f h naught 4. All right, now we also have, I'll do it again here, m dot f, this is f qr plus h naught 2 minus 1 plus f h naught 4. And now we're going to define, remember, h naught as Cp T naught. So we have 0 equals f qr plus Cp T naught 2 minus 1 plus f Cp T naught 4. All right, we're making progress, because now, if you remember from previous steps, we have T naught 2, right? And most of the time T naught 4 is given, QR is given, and so what you can do is you can rearrange this and solve for F. Okay. And where is my paper? When you solve for F, this is the equation you get. T naught 4 over T naught 2 minus 1 divided by QR over Cp T naught 2 minus T naught 4 over T naught 2. Okay? So that is your fundamental F equation that you need to use, which is used to find the performance of these types of air-breathing engines. And so now we can now move on to 4 to 6 and look at that process. So we're from 4 now to 6, and we're going to call this an isentropic expansion to ambient pressure. Okay, so we're going to make sure that the pressure is atmospheric when it shoots out. We don't want it lower, so the minimum we want would be atmospheric, because if you remember from the thrust equation, anything lower than atmospheric, you're going to lower thrust. So we're going to assume T naught 4 is equal to T naught 6, because it's isentropic. P6 is equal to PA. And just remember that P naught A equals P naught 2 equals P naught 4 equals P naught 6, your total stagnation pressure, which this deals with losses. We're assuming ideal. And if we're doing isentropic, we can use that isentropic equation that I showed you in the previous video that relates your temperatures and stagnation values to each other. Okay? This governing equation, you can solve for TE, all right? Because you have P naught 6, you have PE, you have T naught 6, okay, which is equal to T naught 4. You can solve for TE, which is used to solve for your exit Mach number, okay, which then you can figure out your exit velocity, okay. So how do we solve for that? Well, use your stagnation equation that I showed you before. Okay. You can then solve for ME. Okay. So solve for ME. So then use Mach number equation. Oops. Which is ME equals UE over CE, which is UE over the square root of gamma RT E. And we can solve for now UE. Okay. Then you can use the engine performance equations to figure out your efficiencies and your thrust. Okay, here is a video to help you with the homework for Ramjet. So in this particular problem, okay, I give you 100 newtons of thrust, and I want you to find the performance of this inlet, but I also want you to find the inlet and exit area so you can actually like size this ramjet. Okay, so here is the CP, so specific heat at constant pressure that I've been talking about. Here's your ambient or static temperature, your ambient or static pressure, gamma. Here's your gas constant. We're flying at a Mach number of 3. Thrust is 100. And here is our heat reaction of the fuel, that QR value, okay, which is what, 45 million, okay, joules per kilogram K. And then here is our total stagnation pressure in the combustion at 2,500 degrees, or 2,500 Kelvin, okay. So these are the givens in this particular problem. And then here is the inlet, right? We have the density using ideal gas equation, the speed of sound, our inlet velocity using the Mach number relationship, our stagnation to static ratio, okay? Stagnation temperature, gamma P. This equation is your, if I go back to the top, gamma over gamma minus 1, okay? This is your equation that has the static temperature and static pressure. I just found that ratio. Here's your static or stagnation, sorry, your stagnation pressure. Okay. Here's the combustor, T02, which is equal to T0A. Here is your stagnation pressure, okay, which is equal to P0A because there's no losses. Here's your static temperature, okay. We can use the Mach number or the stagnation equation with the Mach number. Here is stagnation ratio. Okay. Here is QR over CP T02. Okay. And then here is that F, which is your fuel air ratio. And then again, your stagnation pressure at 4, which is the same. Here is your exit. So your static pressure, your stagnation ratio, your stagnation pressure, gamma T. Gamma T is just the inverse of gamma P, okay, just for reference. Here is your stagnation to static ratio. The T06 over T04 is 1 because they're the same. Here's your exit temperature. T06 is equal to T04. Here is your exit Mach number, okay, which is found by using this ratio. All right. Speed of sound, or sorry, the speed of sound. Here's your exit velocity. Okay, and then don't worry about this. Just check. This is the ratio of your exit, right, to your inlet, which is used in the engine performance. So here's your propulsion efficiency. Here's your thermal efficiency, your overall efficiency, your static thrust, and your thrust-specific fuel consumption. Okay, so the overall efficiency is not very good for this engine, but That's okay. And then down below here is mass flow rate at the entrance, inlet area, your diameter of the inlet, okay, your exit area, exit diameter, and mass flow rates. Okay. Now, how do I find the mass flow rate? Well, I can take the specific thrust and divide that by, or take your thrust and divide by your specific thrust, okay, that you found. That's your mass flow rate in, okay. And then the area, you just use the mass flow rate equation, which is rho AV, all right, and then you can just convert that. And you do the same thing down here, okay. To find your exit area and your inlet area, okay. So, for this particular homework, take a look. If you have questions, let me know. But this should give you some numbers to compare and check. And you can make it in Excel, you can make it in Octave, you can make it in Python, whatever code or whatever programming language you're happy with.